In section 11.5, we're going to turn our attention to something called vapor pressure. What is vapor pressure? Well, in the last lecture, we learned that under a certain set of conditions, a substance might be a solid or a liquid or a gas. So let's imagine something like water, which is a liquid at ordinary room temperature and pressure. If you were to take a glass of water and not fill it very full, but just set it out on the windowsill or on the counter, and if you left it long enough, eventually that glass would be empty. Where did the water go? Well, the water left because some of the molecules were going into the gas phase and then escaping off into the room. You will also be familiar with this concept if you think about any liquid that has an aroma, has a smell. And there's so many things you might think of, from cleaning solutions like ammonia to all kinds of foods and drinks. If you can smell something, it means that molecules of that substance are making it into your nose. And that can only happen from a liquid if some of the molecules are escaping from the liquid, going into the air and winding up in your olfactory system. Now, if you do this with an open container and you wait long enough, you'll lose all of the substance. But if we do this in a closed container, which is what we show here, let's imagine that we have some evacuated vessel and there's nothing in it, and we're going to now insert or add liquid ethanol. Some of the gas molecules have enough kinetic energy that they can escape from the liquid and go into the gaseous state. But because it's in the sealed container, they can't get away. They're trapped forever kind of in contact with the liquid. There's a certain rate at which molecules escape from the liquid and go into the gas phase. But then what's going to happen is those molecules are going to continue to collide with the surface of the liquid, and sometimes when they hit the liquid, they're going to stick to the other molecules and go back into the liquid phase. So what's going to happen over time is there will be a certain rate at which molecules evaporate, going from the liquid into the gas, and then there's going to be an equal rate at which the molecules in the gas phase stick to the liquid and go back into the liquid. And the rate of the latter, how fast they're going back into the liquid, is going to go up the more molecules we have in the gas phase. Or, to put another way, the higher the pressure. And so pressure will initially rise in this experiment, but it will soon reach a value that is constant. And we call that the vapor pressure of a given liquid. The vapor pressure, by the way, does not depend on how big our container is. It doesn't depend on, to a first approximation, how much liquid is in the container. The only thing that the vapor pressure depends on is the temperature. And why is it that the temperature is so important? We can understand that by going back to a concept from Chapter 10, kinetic molecular theory. So in Chapter 10, we learned that you have a certain distribution of speeds for any given substance at a given temperature. This is for a gas, but we could also apply this same concept to a liquid. At the same time, we might imagine that we have a certain kind of force, an intermolecular force that's holding the molecules together. And for one of the molecules to get away, it has to have more kinetic energy than the forces that are holding it to the other molecules. And this dashed line represents that energy. So what we see is only the molecules that are in the shaded blue region have enough kinetic energy to escape from the liquid and go into the gaseous phase. Okay, so that's going to happen, but at the same time, we're going to have molecules going in the reverse direction and we'll come to a state of equilibrium. If we now increase the temperature, right, what we do is we know that we shift this curve to higher kinetic energies, and it also broadens out. So now in the red curve, which might be at some arbitrarily higher temperature, we can see that we have a greater fraction of molecules that can escape the liquid and go into the gas phase. And that's what causes the vapor pressure to increase as the temperature goes up. We might also think about what happens if we have two different liquids that are at the same temperature but have different intermolecular forces. So here is another way of plotting one of those liquids, similar to what we looked at the last slide. And this shaded purple region here is the fraction of molecules that can escape into the gas phase. If we were to, let's say, magically change the strength of the intermolecular forces, making them weaker, that would shift the minimum energy required to escape the liquid down to lower energies. So this might represent a different substance at the same temperature, but with weaker intermolecular forces. And you can see now that the fraction of molecules that have enough energy to escape has gotten larger. Not because our curve has changed at all, but just because there's a lower threshold for getting away from the liquid and going into the gas phase. So from that, we can conclude that if we have weaker intermolecular forces, less energy is required to escape into the gas phase, and therefore we will have a higher vapor pressure at the same temperature. The inverse of this is also true. Let's imagine instead that we have another liquid with stronger intermolecular forces. So now that's going to shift this minimum energy to escape to higher energies. And consequently, we're going to have a smaller fraction of molecules that can escape into the gas phase. Therefore, when we have stronger intermolecular forces, we're going to have lower vapor pressure at the same temperature. In this slide, we're plotting the vapor pressure of 4 different liquids: diethyl ether, ethanol, water, and ethylene glycol. And those molecules are shown over here. They all contain oxygen and hydrogen, and with the exception of water, they also contain carbon. Okay, these are small organic molecules. Now you can see that there's a definite relationship between the shape of the curve, between the temperature and the vapor pressure. And as the temperature goes up, the vapor pressure goes up, as I promised on the last few slides. We can also see that if we look at the curve for water, when we get to 100 degrees C, right, what is that? That's the boiling point of water. The vapor pressure becomes equal to 760 torr, which is 1 atmosphere. So at the boiling point, the vapor pressure is going to equal the external pressure, and then we will get transition, boiling, into the vapor phase. The other thing we see from these curves is diethyl ether. This molecule is polar, but it cannot hydrogen bond. So that's going to be the weakest intermolecular force. Ethanol has stronger intermolecular forces because we can have hydrogen bonding through this OH group. Water has a little bit stronger hydrogen bonding or intermolecular forces still, because we know that water is going to boil at 100, whereas ethanol boils at 78 degrees C. And then ethylene glycol, right, this is the main component of antifreeze. This boils at even a much higher temperature, so it has even stronger intermolecular forces. And we can see that as the intermolecular forces get stronger, our vapor pressure curves are shifted out to higher and higher temperatures. Now, one vocabulary thing we can say is that if you have a substance that has a high vapor pressure, there's a lot of molecules escaping into the gas phase, we would say that substance is volatile. And ethanol and diethyl ether are both much more volatile than water, whereas ethylene glycol is less volatile. There's a lot of applications of these vapor pressure curves. One of them occurs in the distilled spirits industry. Let's say you want to make something like whiskey or vodka or rum or gin. So you're going to do a kind of a fermentation using yeast typically, not that different from making beer or wine. That's going to give you a solution that has a certain amount of ethanol in it, but it's probably only going to be 10 or 15% ethanol. But if you wanted to make, let's say, vodka, and you want it to be instead 40% ethanol or 50% ethanol, how do you concentrate it? And that's done through distillation. And we're going to take advantage in this process of the fact that ethanol has a lower boiling point than water. So very naively, you might think, okay, if I heat my liquid up to 80 or 85 degrees C, the ethanol is going to boil and the water is not, and it'll get left behind. But what this graph shows us that if you were to heat up to let's say just 80 degrees. Well, yes, you would be boiling off the ethanol, but the water would have a vapor pressure of nearly 400 torr at that temperature, right? So that would be about a half an atmosphere. So there's going to be a lot of water molecules in the gas phase as well. And so in distillation, what you're going to do is you're going to make those gases, which is a mixture of ethanol and water, pass through a very tortuous or convoluted pathway, and along the way you're hoping or taking advantage of the fact that the water is going to condense back into a liquid more readily than the ethanol. So that is how you might do a separation. Of course, if you're making vodka or gin or whiskey, you don't have to separate them completely. You just want to get a partial separation. The idea of distillation is also used in the petroleum industry. If you start from crude oil and you want to make all the different products up to gasoline out of crude oil, you do distillation to separate them. Now, coming back to the idea of the boiling point, for any substance, we can define the normal boiling point as the temperature at which the vapor pressure equals 1 atmosphere. And that's shown with this dashed line in this figure. So you can see here, diethyl ether has a normal boiling point of 34.6 degrees Celsius. Now, it's worth keeping in mind that if we were to change the external pressure in some way, we could change the boiling point. And one example of that might be what happens when you go to high altitude. Okay, so here's a picture from the Telluride Brewing Company, which is in Telluride, Colorado. I've been here a few times. It's a beautiful place. And of course, in the process of making beer, as I said in the last episode, you do have to heat the water up. You heat it up to boiling. And the boil does various things, one of which is extracts bitterness from the hops. But the temperature at which boiling occurs is going to be different in Telluride than it would be in Columbus. How much different? Well, when you go to higher elevations, because there's less of this big column of atmosphere pushing down on you, the pressure goes down. And at 9,000 feet, which is roughly the altitude there, the air pressure is only 540 torr, right? Only maybe about 3/4 of an atmosphere. We might ask, at that high altitude, what's the boiling point of water? Well, we just have to come over here to our vapor pressure curve. Let's find 540 torr, which is about right here. Come over until we get to where it intersects the boiling curve or the vapor pressure curve of water. It's about right here, and so we can see that, all right, ballpark, water's going to boil at about 90 degrees C there, rather than at 100. And if you looked up the value more precisely, you would see that at 9,000 feet, water boils at 91 degrees C, or 195 Fahrenheit. When you're doing processes that depend on boiling, things are going to happen differently at high altitude. And if you ever look at a lot of foods you might get in the store, like maybe a baking or something like that, you'll see that there are special directions for cooking at high altitude because of this. The converse of that is that if you can cook something at a higher pressure, and that's the concept of a pressure cooker or an Instant Pot, then the higher pressure will push the boiling point higher. Because we just learned in the last lecture that when you have the liquid and the vapor in equilibrium, that is, you're in the process of boiling, the temperature can't go above the boiling point. So if you cook something in boiling water, you're going to cook it at, let's say, 100 degrees C if you're at sea level. But if you have a pressure cooker like this, in fact, the boiling point might be 110 C or 120 C. And because of that, things cook faster when you do it under pressure. Another thing we can say is that there is actually a mathematical relationship between the vapor pressure and the temperature, and it's different for every substance, but similar. Okay, and this is the equation. This is called the Clausius-Clapeyron equation. And what we see here is that the natural log of the pressure is inversely proportional to the temperature. And the proportionality constant is the heat of vaporization over the gas constant R. And so what you can see here is that when you have a higher enthalpy of vaporization, that means stronger intermolecular forces. This term here delta H over R is going to be more highly negative. And that means that the pressure is going to be smaller. And if you were to plot the natural log of the vapor pressure versus 1 over temperature, right, you would just get a straight line. And the slope of that line is minus the enthalpy of vaporization divided by the gas constant R. Okay, so in this way, if we do an experiment where we measure the vapor pressure at different temperatures, we can use this data to determine the enthalpy of vaporization. Let's finish with a problem. This is a conceptual problem. So let's imagine that we have our sealed bulb that has liquid ethanol in it. And as we've been discussing in the lecture, some of the molecules from the liquid are going to escape and go into the vapor and build up a vapor pressure. At 298 Kelvin, the vapor pressure in this bulb is going to be 45 torr. Now, if this is connected to an empty bulb, one that doesn't contain any ethanol, and has the same volume and the same temperature, what's going to happen when we open this stopcock and allow the two cylinders to mix, right? So that will allow molecules of ethanol to come over to this side of the container. If we do that and then we let the system come to equilibrium, what is going to be the pressure after it comes to equilibrium? Your answer choices are given below. I want you to make a choice and then come back and we will discuss the answer. Well, what do you think? The natural tendency here is to think that because we're expanding the volume, that the pressure is going to go down, right? If we just had a gas on one side and then we opened the stopcock and allowed the volume to double, we know from Boyle's law in chapter 10 that the pressure would go down by a factor of 2. But that's not what's going to happen here. The answer is the new pressure will still be 45 torr. Why is that? Well, when we open the stopcock, ethanol molecules from this side are going to go over to the other side. And so initially you probably would drop the vapor pressure, maybe to something close to 22.5 torr. But now the system is out of equilibrium for the temperature here. So the rate at which gas molecules are colliding with the liquid has now decreased. And so because of that, the rate at which molecules go back into the liquid phase has gone down. To compensate for that, then we're going to have a period where more ethanol is going to escape from the liquid into the vapor phase. And that will go on for a while until we get back to this same pressure of 45 torr. Because remember, the vapor pressure of a liquid depends only on the temperature, not on the volume of the container, not on the amount of liquid, but just on the temperature. So the answer is 45 torr.